And new tonight, an Idaho mountain climber is dead after falling from a jagged peak in Wyoming's Grand Teton National Park.
We're tracking a major cash infusion for restoration projects in Yellowstone and Grand Teton National Parks.
Cracks have been discovered beneath the Grand Teton, prompting the United States Geological Survey, USGS, to issue a red alert, its highest level of geological warning. This alert has stirred immediate attention from scientists, emergency management teams, and the public alike as the implications reach far beyond the rugged wilderness of Wyoming's iconic mountain range. The sudden and alarming geological shift has drawn scrutiny not only because of its location in one of America's most beloved national parks, but also because of the broader seismic and volcanic threats that it may signal. Before we start, smash the like and subscribe buttons for more updates. The Grand Teton, standing at over 13,700 feet, is part of the Teton Range, an awe-inspiring series of peaks that dominate the skyline of northwestern Wyoming. These mountains rise dramatically without foothills, a hallmark of intense geological activity over millennia. What makes this situation especially concerning is the Grand Teton's proximity to the Yellowstone caldera, one of the most seismically active and geologically volatile regions in the world. The Teton Fault, which runs along the base of the range, has long been a focus for geologists monitoring potential movement in the region. This fault is capable of producing large earthquakes, and recent findings indicate that it may be experiencing a significant period of stress. The appearance of deep subsurface cracks is not an isolated anomaly. Over the past few weeks, scientists have recorded an uptick in microseismic activity under the Teton Range. While these tiny tremors are not felt on the surface, their frequency and pattern can provide important insights into the stress dynamics below. In this case, the tremors have coincided with the discovery of long, irregular fissures that stretch underneath the Grand Teton, detected through advanced ground-penetrating radar and GPS deformation sensors. The concern is not merely cosmetic or superficial. These fractures point to a shifting, unstable foundation beneath one of the most picturesque regions of the Rocky Mountains. What makes this development even more concerning is the unusual nature of the seismic data coming from the area. Researchers have noted that the movement detected is not typical of regular tectonic slipping. Instead, the pattern suggests that magma could be forcing its way upward through the Earth's crust. While it's not confirmed whether magma is actually involved, the signs, such as elevated gas emissions, ground uplift, and thermal anomalies, strongly hint at volcanic activity. If magma is indeed rising, this could suggest a connection between the Grand Teton fractures and the broader Yellowstone volcanic system. The Yellowstone supervolcano, sitting just 60 miles northeast of the Grand Teton, has been the subject of intense scientific scrutiny for decades. Capable of producing eruptions thousands of times more powerful than Mount St. Helens, Yellowstone's last major eruption occurred over 640,000 years ago. Since then, it has experienced numerous smaller eruptions and hydrothermal explosions. Any indication that tectonic activity near the Grand Teton could influence or be influenced by Yellowstone's magma chamber is taken extremely seriously by the USGS and affiliated monitoring agencies. Issuing a red alert is not a routine action. It signifies that a geologic event is either underway or imminent, and that it could result in significant disruptions to local populations, infrastructure, and ecosystems. The Grand Teton National Park is not only a wilderness sanctuary, but also a heavily trafficked tourist destination, especially in the summer months. Tens of thousands of people visit weekly to hike, climb, camp, and photograph its stunning peaks. An evolving geological threat in such an area demands swift coordination between park authorities, scientific agencies, and local governments. The initial response to the alert has been a comprehensive assessment of the physical area. Satellite imaging, aerial surveys, and field expeditions are being deployed to monitor every inch of the park for additional signs of deformation, landslides, or new surface cracks. One of the more immediate concerns involves the potential for large-scale landslides. With the steep vertical relief of the Teton Range, any disruption to the subsurface could destabilize massive rock faces, triggering avalanches or rock falls capable of devastating campgrounds and hiking trails below. Hydrological impacts are also under intense observation. The Teton Range plays a critical role in the regional water cycle, feeding the Snake River and other tributaries that support agriculture, wildlife, and communities downstream. Cracks beneath the mountain could alter the flow of groundwater or redirect natural springs, with consequences for both ecosystems and human usage. Additionally, the presence of hot springs and geysers in the surrounding area adds another layer of complexity. These hydrothermal systems are often sensitive indicators of subterranean magma movement and could respond violently if pressure builds in unexpected ways. The red alert has also triggered a reassessment of seismic preparedness throughout the Intermountain West. Municipalities as far away as Salt Lake City and Denver are evaluating their readiness for a possible earthquake cascade. The interconnected fault systems that stretch across the region mean that activity under the Grand Teton could have ripple effects. Although the immediate threat is localized, geophysical systems do not respect political boundaries, and what begins as a fissure in Wyoming could translate to tremors or shifts hundreds of miles away. Of particular scientific interest is the interaction between tectonic stress and magma pressure in the region. Some geologists propose that these cracks may be forming as a result of what is known as dike intrusion, a process where molten rock forces its way through layers of brittle crust, creating new fractures as it goes. This is a common precursor to volcanic eruptions in other parts of the world. If similar dynamics are occurring under the Grand Teton, it would represent one of the first such documented events in this specific area, and could redefine how scientists understand volcanic risk in the broader Yellowstone region. The emotional impact of the discovery cannot be underestimated either. For many, the Tetons are not just geological formations, but symbols of rugged natural beauty, solitude, and Americana. The idea that something so grand and seemingly immutable could be threatened by hidden forces deep beneath the earth shakes the public's perception of permanence. It's a reminder that mountains, no matter how majestic, are not eternal. They are dynamic, ever-changing, and deeply vulnerable to the forces of the planet. Tourism authorities have already begun issuing advisories, warning visitors to remain on designated trails, avoid steep or unstable areas, and report any unusual signs such as steam vents, gas smells, or rumbling sounds. Scientists on the ground are using portable sensors to map micro-earthquakes in real time, while drones equipped with thermal cameras scan the upper reaches of the mountain for heat signatures that might indicate subsurface magma activity. Every data point gathered could be a crucial clue in unraveling what is happening beneath the surface. What complicates the situation is that these kinds of geological warnings don't always lead to dramatic outcomes. Sometimes a fault may release pressure without a major quake. Sometimes magma intrudes and then cools without erupting. But the fact remains, the presence of cracks under the Grand Teton is not normal, and it has occurred in a context of rising seismic activity, ground deformation, and heat anomalies. That combination is why the USGS acted with urgency. Even more pressing is the need for modeling and forecasting. Using supercomputers, scientists are running countless simulations to determine what might happen next. Could the cracks widen and trigger a localized collapse? Could they set off a chain reaction of seismic events along the Teton Fault? Could they be the early indicators of a volcanic awakening in a system long thought dormant? The models are only as good as the data they are fed, and so every tremor, every shift, every gas reading becomes a critical piece of a growing puzzle. The region's indigenous communities are also being consulted, both out of respect and in search of historical patterns. Oral histories from tribes who have lived in the shadow of the Tetons for generations sometimes contain references to earth-shaking events, smoke rising from the mountains, or changes in wildlife behavior. While not scientific in the modern sense, these stories can offer valuable context or align with long-term geological timelines in surprising ways. Insurance companies and property developers in nearby towns like Jackson are now confronting the implications of this alert as well. If the geological threat escalates, it could dramatically affect property values, tourism revenue, and regional development plans. Infrastructure such as bridges, roads, and tunnels in the area are being inspected for vulnerabilities. Emergency evacuation routes are being reviewed, and shelters are being prepared, just in case. Wildlife biologists have also reported strange behavior among local animal populations. Herds of elk, deer, and bison have been observed migrating earlier than usual or altering their traditional paths. Some birds have shifted nesting grounds, and insect activity in geothermal areas has changed. While none of these signs are definitive proof of geological activity, they often precede major events in nature, serving as a form of biological early warning system that humans are only beginning to understand. One of the most gripping elements of the current situation is the sense of uncertainty. With cracks spreading beneath the Earth's surface and seismic instruments registering unpredictable tremors, everyone, from scientists to hikers to local families, feels the tension. It is the uneasy pause before something unknown. Will it be an earthquake? A volcanic event? A harmless settling of the crust? Or something no one has predicted? What's unfolding beneath the Grand Teton may ultimately rewrite scientific understanding of the region. It forces a confrontation with the deeper mechanics of the Earth, those ancient invisible forces that occasionally make themselves violently known. It challenges assumptions and demands respect for a planet that, despite centuries of study, still guards its secrets fiercely. Whether this moment marks a prelude to eruption, a warning tremor, or simply an unusual but benign shift, it has already etched itself into the geological record as an event of significance. The cracks beneath the Grand Teton are not just physical fractures, they represent a break in complacency. They call attention to the living Earth beneath our feet, an Earth that can rise, fall, open, and burn with little notice. For now, the mountain stands tall, but deep within its foundation, ancient forces are at work, and the world watches closely, waiting for the next sign. As the red alert remains in effect and scientific investigations intensify, the situation beneath the Grand Teton continues to evolve in complexity and urgency. The initial discovery of subsurface cracks has rapidly escalated into a broader examination of deep earth processes at play beneath one of America's most iconic mountain ranges. With each passing day, new data flows in, painting a picture of a geological system that may be approaching a threshold, one that no one can precisely define. At the heart of the investigation now is the question of energy buildup. In tectonically active zones like the area surrounding the Teton Range, stress accumulates along faults and fractures until it is suddenly released, either through seismic shaking or, in rarer cases, volcanic activity. The energy doesn't always discharge in catastrophic events, but the potential is always there. In this instance, the geometry of the discovered cracks, some of which extend at steep angles downward into the crust, has drawn particular concern. Their orientation and depth suggest they may be acting as conduits for deeper pressures, possibly linking with more extensive underground fault systems or magmatic intrusions previously undetected. Researchers have now begun incorporating geodetic techniques to understand how the landscape itself is shifting. Using satellite-based INSAR interferometric synthetic aperture radar, which detects ground displacement at millimeter-level precision, scientists have mapped slight vertical uplift across certain areas near the base of the mountain. This uplift could indicate that pressure is mounting below, pushing the surface upward ever so slightly, a subtle yet significant warning sign. While these deformations may not be visible to the naked eye, they are being watched around the clock by teams from the USGS, NASA, and several university-led geophysics labs. Compounding the unease are changes in the region's thermal output. Aerial infrared scans have detected a rise in surface temperatures in several zones across the southern and eastern flanks of the range. These are not standard wildfires or sun-warmed rocks, but temperature anomalies that hint at increased geothermal flux. In simpler terms, something is heating up underground. This heat may be related to hydrothermal fluid movement, or more ominously, to molten rock approaching shallower depths. Teams of volcanologists and structural geologists have now converged on the area, bringing with them sophisticated instruments designed to monitor gas emissions in real time. In active geological zones, gases such as sulfur dioxide, carbon dioxide, and hydrogen sulfide can provide early indicators of magmatic movement. Over the past week, sensor arrays have picked up measurable increases in carbon dioxide emissions near specific fracture zones. This may suggest degassing, an early phase of magma ascent where volatile compounds escape from rising molten rock, sometimes long before an eruption occurs. The newly gathered gas data, while not conclusive, has deepened concerns about the interconnected nature of the area's subterranean systems. Some experts are now drawing comparisons to other caldera systems around the world, such as Campi Flegrei in Italy or Taupo in New Zealand. where surface deformation, gas release, and seismic swarms often precede larger-scale events. While no two volcanic systems are exactly alike, these parallels offer useful templates for anticipating what might happen next under the Tetons. Geologists are now drilling core samples near the fissures to study rock temperature, stress conditions, and chemical alterations caused by migrating fluids. These samples can tell a detailed story of what's happening beneath the surface. Elevated temperatures or hydrothermal alterations in the rock's mineral structure could validate the rising magma hypothesis or point toward a different mechanism, such as fluid-induced fault weakening, which could still precipitate earthquakes or collapses even in the absence of molten material. One of the most critical aspects of the current red alert scenario is the risk of cascading hazards. Cracks in the subsurface may not only destabilize sections of the mountain, but also disrupt the glacial systems that cling to its upper elevations. The Tetons are home to several small but significant glaciers, which play a vital role in regional hydrology and ecology. Should the ground shift beneath or near these ice masses, it could trigger glacial outburst floods, sudden surges of water capable of carving destructive paths through the valleys below. Moreover, as snow and ice melt due to geothermal anomalies, the volume of water seeping into the newly formed cracks increases. This can act as a lubricant, reducing friction along fault planes and potentially increasing the likelihood of slippage. In seismically active areas, the presence of water can be the tipping point that transforms slow tectonic creep into sudden violent rupture. Scientists are now tracking water movement through LiDAR mapping and high-resolution hydrological sensors installed throughout the park. The broader ecological consequences of such a disturbance are also becoming a growing focus. The region is a biodiversity hotspot, home to species whose survival depends on delicate seasonal balances. Disruption to soil temperatures, water availability, or terrain stability could lead to a collapse in some of these finely tuned systems. Alpine plants, which rely on stable conditions to flower and propagate, may suffer widespread die-offs if the ground continues to move or temperatures rise just a few degrees more. Animal populations, including sensitive species like pikas and mountain goats, may be forced to migrate, if they can. Of particular note is the impact on avian life. Recent surveys have indicated a drop in nesting activity among cliff-dwelling birds such as peregrine falcons. Biologists believe this could be a reaction to low-frequency seismic noise that is imperceptible to humans, but detectable by animals sensitive to vibration. These changes, though subtle, could serve as an important indicator of coming changes, especially if they align with ongoing geological events. Amidst these multifaceted developments, emergency response planners are undertaking what might be one of the most challenging logistics exercises in decades. The terrain around Grand Teton is remote, rugged, and difficult to evacuate on short notice. The potential need to move thousands of campers, climbers, and park personnel within hours requires detailed route mapping, coordination with search and rescue teams, and the establishment of airlift protocols in case access roads become impassable. In nearby towns like Jackson Hole and Teton Village, local leaders are holding daily briefings with geologists, law enforcement, and public health officials. Schools have initiated emergency drills, and local hospitals are being stocked with supplies in preparation for possible mass injuries related to rockfalls or landslides. Temporary shelters are being readied at community centers and churches, complete with power generators and satellite communications in case the region loses connectivity. Despite the tense atmosphere, the scientific community views this moment as a once-in-a-generation opportunity to learn. The ability to study an active geological shift in real time, with the full arsenal of 21st century technology, provides an unprecedented chance to deepen understanding of tectonic processes, magma movement, and earthquake forecasting. Dozens of peer-reviewed studies will likely result from this episode, advancing fields from geochemistry to seismology. Another unique factor in the current situation is the public's involvement. With open-source seismic data, live satellite feeds, and real-time gas sensors available online, curious citizens and amateur geologists are now participating in the monitoring effort. This democratization of data creates both opportunities and challenges. While it allows for broader engagement and faster reporting of anomalies, it also opens the door to misinformation and panic. Authorities are urging the public to rely on official channels for updates and avoid circulating unverified rumors or conspiracy theories. Public trust is being carefully managed. Park rangers and USGS representatives are holding town hall meetings and live stream Quanda sessions to explain the science behind the red alert, clarify what is known and unknown, and set expectations. The emphasis is on transparency without creating unnecessary alarm, a difficult balance to strike when the Earth itself seems to be sending signals of change. Looking ahead, the next steps hinge on the pace at which the situation develops. If deformation continues to intensify, emergency evacuation may be enacted in stages, prioritizing high-risk zones first. Should the gas emissions stabilize and seismicity taper off, the alert level may be downgraded. Though scientists warn that a lull is not always a sign of reduced danger. In volcanic systems, quiet periods can sometimes precede major eruptions as pressure builds silently beneath a temporary crust. For now, the Grand Teton stands unchanged in outward appearance, its snow-draped summit glinting in the summer sun. Tourists still gather to photograph its iconic silhouette, unaware in many cases of the silent drama unfolding miles beneath their feet. But those monitoring from behind screens in research labs and field stations know that landscapes can change in the blink of an eye. Mountains rise over eons, yet they can collapse in seconds. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on cracks under the Grand Teton? Natural or alarming? We want to hear from you. Thank you for watching, and see you next time.